So listen, guys, for this nature of matter unit test tomorrow, we started off this unit talking about Thomson. And we didn't spend very much time talking about Thomson at all. All you got to really remember for this guy, Thomson, J.J. Thomson, 1897, was that he discovered the electron. You don't need to know any details about how he discovered the electron. You don't need to know some of the properties that he discovered. He didn't find a charge or mass or anything really important like that, but he did discover the electron by measuring one of the properties of the electron. And we're not going to really go into that, but know that it wasn't one of the ones that you would be familiar with. Okay, it wasn't the charge or the mass or anything like that. Just know that he discovered the electron, and for whatever reason, you don't need to know why, but for whatever reason, he's given credit for the discovery of that electron. Next, we went to Millikan, and this is where we spent some time, right? A couple of days on Millikan. On your unit test tomorrow, I believe there's 3 questions on the Millikan oil drop experiment. Really, it boils down to 2 different situations, right? When we have a charged particle, an oil droplet that is either suspended between 2 plates or traveling at a constant velocity, or it could be accelerating between the 2 plates, for the top plate or the bottom plate. So we might see something that looks like this, with the top plate being positive, or we might see something that looks like this, with the top plate being negative. Or, listen, we might even see it not even drawn as a diagram, but just given to us in a word problem. If it's given to you in a word problem, you should draw the picture. Every single time you should draw the picture. Now, there's 3 really important variables that we talked about here. There's 4 variables, but 3 really important ones that you should always focus on. The first one is the electric field. Draw that in to your diagram every time. The electric field here in this first diagram with the top plate being positive is which way? Is it pointing upwards or downwards, the electric field? Downwards. Yeah, the electric field always points away from the positive and toward the negative. And this one, it's going to be pointing upward, away from the positive, toward the negative as well. So always draw in that electric field. That's the first of the 3 critical variables here. Now, we need to draw a charged particle, a couple charged particles before we do anything else. We're going to make one of them in each diagram a positive charge and one of them a negative charge. It's also important that you recognize the nature of the charge. That's the second really important variable, the nature of the charge, whether it's positive or negative. And finally, the third important variable, the third critical variable, I should say, is the direction of the electric force. Which way is the electric force acting on this positive particle right here, this first positive particle? Is that going to be up or down? Downwards? I was trying to know that electric force is acting downwards. Good. Good. If we have a positive particle, the force is with the field. Are you sure? I'm positive the force is with the field. So that third critical variable is that downward electric force. So 3 critical variables here: the electric field, the nature of the charge, and the direction of the electric force. Now, what's going to typically happen here is that you're going to be given 2 of those, or you'll have available to you 2 of those, and you're going to find the 3. What often happens is that you have the force and the field, and from that you're going to determine the nature of the charge. Now, there is a direction of electric force on this one. This one's going to be upward. The electric force is opposite to the field for a negative particle. It's going to be upward here because it's with the field, and it's going to be downward here because it's against the field. Now, the force of gravity, that's important too, but that's not one that I consider one of my critical variables, because the force of gravity is always acting down. So we draw that down no matter what. It's important in terms of direction and so on, but it's not going to help us to determine the nature of the charge or the direction of the field and so on. Now, there's 2 situations that arise here for these 3 questions that you're going to see on the oil drop experiment. The first one is when the charged particle, the oil drop, is either suspended or traveling at a constant velocity. When it's suspended or traveling at a constant velocity, we're in a state of, what's the word? Starts with an E? Equilibrium. Yes, we're in a state of equilibrium. And when we're in a state of equilibrium, we know forces must, starts with a B, balance, right? So we're going to set those 2 forces equal to each other, or at least the magnitudes of those two forces equal to each other. Fe equals Fg. We're going to replace Fe with Q times E. Be careful. It's not QV. QV is energy. QE is force. And the force of gravity is M times G. Now, sometimes, I'd say probably about half the time, we've got to find the electric field because we don't know what it is to sub into there. How are we going to find that? The typical way, at least, that if we don't have the electric field, we're going to find it. This goes back 3 units ago, but we talked about it this unit too a few times. Yeah, delta V over delta D. Remember, that's not change in speed. That's potential difference divided by the distance between the plates. And then typically what we're going to do here is solve for charge. And that charge, as you know, is either going to be (1.60 times 10 to the minus 19 coulombs). That's the elementary charge, which also corresponds, by the way, to the charge of the electron. Or, I shouldn't say that, because the charge of the electron is not the elementary charge. It's -1 times the elementary charge, right? -1 times 1.6. By the way, if you see a question that says the charge is 8e, that just means it's 8 times the elementary charge, or -3e, it just means it's -3 times the elementary charge. Now, the second conclusion we draw from finding that charge is that it's either 1.6 times 10 to the minus 19, or it's a multiple of that. 3.2, 4.8, 6.4, 8.0, 9.6 times 10 to the negative something. In other words, charge is, what's that keyword? Or so that Q word? Charge is quantized. Just like coins are quantized, right? You can have a nickel, or you can have 13 nickels, but you can't have 12.5 nickels. You can't have 63 cents in Canada in cash. It's impossible. Now the other situation is when we have an accelerating charge. You got to figure, if I'm giving you 3 questions on the oil drop experiment, you got to figure you're going to see at least one where the charged particle is suspended or traveling at a constant speed, and at least one where the charged particle is accelerating, either upwards or downwards. When it's accelerating, we're going to say F net is equal to the sum of the forces. This is the part that the physics 20 student can do, right? Fe plus Fg. Now, this is pretty much where it would end for the physics 20 student. But they know enough to say the net force is the sum of the forces. We're going to replace F net with M times A. We're going to replace Fe with Q times E, Q times the electric field, plus M times G. And we might have to solve for E. Right? We might have to solve for E using delta V over delta D. Most times, you're going to end up solving for Q. And it will be either 1.6 times 10 to the minus 19 or a whole number multiple of that. Just watch the signs here, okay? Just watch the signs. The acceleration will be positive. Oops, can't even read that. Will be positive if it accelerates up. It will be negative if it accelerates down. So pay close attention to that. You got to remember if you got a problem where it accelerates downward tomorrow, but if it does and you skip that negative on that acceleration, you're going to get that question wrong. This one, the electric force, well, that can be positive or negative because, well, look over here, it's negative, positive, positive, and negative. But that force of gravity, that's always going to be negative because that's always acting down. And finally, when you're solving for charge, sub your numbers in there first. This gets a little ugly if you try to rearrange it without subbing numbers in. Okay, sub your numbers in first and then rearrange it. The first thing you're going to do is take over the M times G. Right? Get rid of what's not attached. Solving for Q, don't get rid of the E first. Get rid of the mg. Take it over to the other side, and then divide by the electric field. It gives you the charge. If you get a number that's 1.6 or a multiple of that, you can be pretty confident you got the right answer there. And then it comes down to is it positive or negative? Right? It's positive or negative. And that's when you look at your field and your force. If they're in the same direction, it's a positive charge. If they're opposite directions, it's a negative charge. Good? All right, well, there's 3 questions. There's 15% of the test right there for you. Next thing we talked about was the radioactivity. There was a few things that we did with radioactivity. There was the whole intro to it. What is it? The ionizing radiation and the properties of these different types of ionizing radiation. And then we talked about transmutation. And then we talked about half-life and the half-life graphs. So the first thing we'll go over is the properties of radioactivity. It's that natural process, a spontaneous process, that random process. It's a quantum process whereby a nucleus decays into something else. We had 4 types that we learned about, at least. There was alpha decay. There was beta minus decay. There was beta positive decay. And there was gamma decay. Remember, this alpha particle is not the daughter nucleus. This is not like the main part that's produced here in alpha decay. It is the small chunk that breaks off to make the bigger part more stable. And this small chunk that breaks off, this alpha particle, or this helium nucleus, because it's really the same thing, this positively charged, right, because it's a nucleus, this positively charged helium nucleus is ionizing. What did that mean, by the way? Ionizing? Turns atoms into ions. What's an ion? A charged element, which can create chemical reactions that are supposed to happen. Beta negative? That's the same thing as a what? By the way, feel free to speak up at home, eh? Just pipe in. You don't even have to raise your hand. Just pipe in. Feel free to speak up if you're here, too. You don't even need to raise your hand. Oh, there's somebody. Oh, there's somebody there. Who was that, Noah?
Luke.
Oh, Luke. What is this also known as, Luke? A beta particle is an
Electron.
Good. It's an electron. What happens is in the nucleus, a neutron changes into a proton and an electron. Exactly the same thing. That's a negative particle, by the way, because of course it's an electron. 0 minus 1 beta, 0 minus 1 e, doesn't really matter. Call it whatever you want. Whatever symbol you want. 0 plus 1 beta, that's the same thing as 0 plus 1 e. What's the other name for a beta positive particle? Beta negative is an electron. A beta positive is, by the way, it's a positive charge. It's not a proton. So what is it? A positron. Yeah, that's a positron. If this is matter, and this is matter, then the positron is antimatter. And the gamma ray, well, that's the easy one because it's not positive or negative. There's no protons, no electrons. There's no other name for a gamma ray. It's just energy, just electromagnetic radiation. Now, finally, we rank these in terms of the penetrating power and the ionizing power. We're going to rank these, 1 being high. 1 being high. Now, the alpha particle has, if you remember, for one of these properties, it's a 1. For one of these properties, it's a 3. Everything's backwards, right? So it goes 1, 2, 3, 3, 2, 1. Remember which one's which? Does an alpha particle have a high ability to penetrate matter, or does an alpha particle have a high ability to ionize matter? It's one or the other. A high ability to ionize matter. Good. So we'd rank alpha particles as a number 1 for ionizing, beta particles would be number 2 for ionizing, and gamma rays would be number 3 for ionizing. Now, in terms of penetrating power, it's exactly the opposite, right? Gamma rays have the highest ability to penetrate matter, and alpha particles have the lowest ability to penetrate matter. Just so you know, the reason that this is the case, when we look at these particles, what's the big difference between an alpha particle and a beta particle? Like one's positive, one's negative, whatever. The biggest difference is 2 of them between alpha and the other particles. One of them is charge. Look at the charge here. Like you got 2 protons in an alpha particle, right? So it's plus 2 elementary charges. That's twice as much as a beta particle, and infinitely more than a gamma ray. So the charge on an alpha particle isn't necessarily crazy high, but it's relative to the beta particles and the gamma rays, it's pretty high. And the mass, look at the mass of the alpha. Like it's only 2 protons and 2 neutrons. That mass isn't very much at all, right? But compared to a beta particle, it's thousands of times the mass of the beta particle. And it's infinitely more than the mass of the alpha particle. That's why the penetrating power of an alpha particle is actually so small, because of its relatively high charge and relatively high mass. And because its penetrating power is so small, that's why its ionizing power is so big, because it stops so quickly and that energy is dissipated so quickly. So the charge and the mass give it a low penetrating power, but the penetrating power gives it a high ionizing potential. All right. Next thing we did was, along with radioactivity, along with the properties of radioactivity, was transmutation. And that's just the equation that describes the conversion of one element to another. I just got a few examples that I wanted to go through with you here today. If you can do one, you can pretty much do them all, but I will caution you to be careful, especially with the beta decay, the beta positive and the beta negative. Those are pretty common mistakes when you're adding instead of subtracting, or vice versa here. Here's the first one. I've got uranium-238, which is naturally radioactive, decaying by alpha decay. I'm going to write it this way, actually. Is that okay? 42He? Sure. Alpha particle is the same as a helium nucleus. Plus, what else? 2 plus what is 92? 90. And 4 plus what is 238? Listen, this sounds silly, guys. Like, you're probably going to be able to figure out 4 plus 234 is 238. But you're allowed to use calculators, especially when you're dealing with a beta particle and you got a -1 in there. If you're going to get mixed up with that, just use your calculator. I mean, it sounds silly to use your calculator for this, but if you're kind of struggling a little bit with whatever, subtracting or adding or whatever, just pull out the calculator. Because you're at home, nobody's going to really see that you did that. Nobody's going to make fun of you for using your calculator for that. And by the way, what is this? How do we know what atomic number 90 is? Where do we find that? It's on a periodic table, right? There's 2 numbers on your periodic table always. There's a big number and there's a small number. The big number you will never in physics 30 pay attention to. It's always going to be the small number. That, I think, works out to be thorium. So on your periodic table, you would see that atomic number 90 is thorium. Is there anything else that's produced there as well? Neutrinos, antineutrinos? Not with alpha. Next one. I got 3 of them here. Carbon-14 decays by beta decay. I could write 0 minus 1 beta, 0 minus 1 E, doesn't really matter. Plus what? 0 plus 14 gives me 14. Minus 1 plus, what is it here? Is it 5 or is it 7? And again, you guys at home can feel free to speak up. Thank you, Luke, for speaking up before. What is it? 7. You look on your periodic table. Remember, again, for this number, the small number, not the big one, the small number, and that small number ends up being, I believe, nitrogen. Is there anything else produced there? Yeah, what is it? Yes, that would be the antineutrino. The antineutrino goes with beta negative. Somebody this morning said, is it always with beta negative? Is there always an antineutrino with beta negative? Always. Every single time there should be an antineutrino with beta negative. Now the bottom one, you can probably guess what that's going to be. Magnesium-23 undergoes beta positive decay. Plus, so there's a beta positive particle emitted, plus what else there? 0 plus 23 gives me 23. And then, Wait a second. 1 plus what gives me some? Listen, we got to know what number this is, right? We have to know what number the atomic number is for magnesium. And we're going to look on a periodic table for that. Eilish, what is it? It's cut off. All right. Pretend you looked on your periodic table. You found that that number was 12. Just write it down. The smaller number again, not the bigger number. You're never going to use that. The smaller number is 12. So we're going to say 23 plus 0, sorry, 0 plus 23 is 23, plus 1 plus 11 gives me 12. And when we look at atomic number 11, I think on your periodic table, I know I'm not going to ask Eilish because that part's cut off, off of the periodic table. I believe it's sodium, isn't it? So you're going to find that atomic number 11 on your periodic table, and you're going to identify that that's sodium from that. Anything else produced there? What is it? Neutrino, yeah. It's going to be a neutrino produced there. And again, we always get the neutrino going with the beta positive K. Always, 0 exceptions. By the way, guys, I wrote down magnesium 23. I wrote it down like this. You guys know to look on your periodic table for the smaller number. Sometimes magnesium 23 can be written like this. If you see something written like this, that number that follows the element is always the mass number or the nucleon number, not the atomic number. You're never going to see it written like this, magnesium 12, because your periodic table can tell you that number. The number that you need to be told is the mass number or the nucleon number. So if you see it written like this, then say, okay, I know that that represents magnesium 23, and then check your periodic table to find that the atomic number is 12. It's a little notation thing, right? It doesn't change the way we do things, but the notation can be important. We don't want to go mess up a question because we're unfamiliar with the notation that we see there. And by the way, listen carefully to this. I think this does happen once on your test tomorrow, I think. Way back in the early 2000s, we had a different curriculum than we have now. They switched it around 2008, I think it was. So we're going on this one for about 13 or 14 years. In the old curriculum, we didn't have to teach about beta positive decay. It was only beta negative decay. So as far as students were concerned 15 years ago, there was no such thing as beta positive. There clearly was. It's just that students in grade 12 didn't know about beta positive. So sometimes you see a question still to this day that I will give you from an exam that was 20 years ago. And it might just say beta decay. It might not say whether it's beta negative or beta positive. If it doesn't specify beta negative or beta positive, that's because it's from an old exam when you didn't know anything about beta positive. So if you see that, and I think you do once tomorrow, assume beta negative. That's what's meant by that, okay? You can always ask me that question if you're unsure, but it is safe to assume if it doesn't specify beta negative or beta positive, that it is beta negative. Get that? All right. Next we did half-life. Still on radioactivity here. Radioactivity is a pretty big thing, actually, for us. In fact, when I look at the number of questions in radioactivity, holy cow. 1, 2, 3, 4, 5, 6 or 7 questions on radioactivity between transmutation and between the properties and between the half-life. It's 6 or 7 questions out of 20 questions. That's your test tomorrow, 20 questions. Okay? It's like a game, right? You guys know that game, 20 questions? Yeah? Where you have to answer yes or no? It's just like that, except you have to answer A, B, C, or D instead of yes or no. So it's just enjoy yourself tomorrow. Play a game for an hour and a half. Half-life. 2 equations. This one's not on your data sheet. So we'll star that one. N stands for the number of half-lives. That's important because we absolutely need that number if we're going to use the other equation. N is equal to n sub 0, 1/2 to the little n. So what happens a lot is that we have to solve for little n using the first equation and then solve for big N or big N0 using the second equation. Remember what we said, guys? Time, whatever units you want, but you'll recognize them. Sometimes we don't recognize a unit. It's just unfamiliar to us. If that's the case, it's either going to be N0 or N. So it's unfamiliar unit, N or N0. If it's a familiar time unit, then of course it's going to be T or T1/2. So again, a lot of times we have to take this number and sub it in here. Not always, but a lot of times. The other situation that arises is when we look at this equation, we write down this equation to solve for little n. Everything fits, except we have to solve for little n, which is more challenging here because we can't just use algebra to do this. And solve for little n, we either use logarithms or what I like to do, which is our divide by 2 method. We're going to say, look, after 0 half-lives, you get 100%, or whatever your initial amount is, 100% or 28 grams, or whatever your initial amount is. After 1 half-life, you got 50% or whatever. 2 half-lives, 25, and so on and so on and so on. Just keep dividing by 2. And if the question says, how much time until you're left with 6.25%, just keep dividing by 2 until you're down to 6.25%. Then you take that number of half-lives, and then probably at that point, probably going to sub it into this equation to solve for either T or T1/2. You guys good with that? There is, I believe, one question on a half-life graph as well. By the way, if anybody needs me to pause it so you can write something down, just ask me to do that. If you're still there at home. The one thing I can tell with it, it's nice to have people in class here. It's hard actually to go back and forth between in class and online here. It's way harder than it was a month ago when we were just full online. This is way harder, at least for me, when we got people in both places. But at least when we have people here, at least I can see at least 4 people are still here and still awake, more or less. All right, whenever we have a half-life graph, it's going to look like this, N and T on the x-axis, and the shape of it's always going to look like this. And we're going to have to do one of 2 things. Or both of those 2 things, maybe both. What are we going to do here? There's no calculations of significance to do here. We're either going to go over and down. So if you have an amount and you want to find out how much time, if you want to find a time, then you're probably going to go over and down. If you want to find an amount, then you're probably going to go up and over. And sometimes we actually do have to use this equation as well, along with the up and over and down. But please, for heaven's sakes, guys, do not use this one. Do not use this one. Like, that's a good equation, an important equation, but not here. Okay, that's an equation that allows us to predict what we're going to see, what's going to happen, and this graph tells us not a prediction as to what's going to happen. The graph is meant to tell us what has already happened. So the predictions often match up with reality, but not necessarily. So don't use this equation that relies on probability. Use your graph that is already established what happens. So use the first one, don't use the second. There's one question on that. Then we talked about fission and fusion. What time is it here? 1:13. Getting there. What topic was that? Number 4? Am I on number 4 here? I don't have it numbered on my page. 4, fission and fusion. What type of reaction is this? Clearly it's fission or fusion, right? Which one of the two is it, fission or fusion? Keep looking out here, but you guys can speak up too. You know what we should do? You know how I should encourage people to speak up? It's like encouraging people to get vaccines. Let's offer $1 million. No, I can't do that. If I win that $1 million, by the way, I have been vaccinated and I've already entered that contest. If I win that $1 million, just so you know, oh yeah, you know what, I was going to get you something, but I won't have you then. So never mind. I'll just keep it myself. I'd like to buy you something, but you know, you won't be around anymore. Well, not like you'd be around, but not around. Anyways, this is what is it? Fission or fusion? Yeah, it's fusion, and you know it's fusion because you have two things becoming one. There's something else produced here, by the way, as well. Let's go to the bottom. 1 plus 1 is 2. 2 plus 0 is 2. 2 plus 3 is 5. 4 plus 1 is 5. So that's going to be a neutron, right? And it's only going to be one neutron. It already balances it. Here's the other type of reaction that we have. This is obviously going to be a fission reaction, right? Fusion is when two lighter elements become one heavier, and fission is when one heavy nucleus becomes two lighter nuclei. So one splits up into two. Let's finish balancing this, okay? 92 on the left side, 90, oh wait. What's the atomic number for ZR? Alex, what is it? I should get a periodic table here. I should get a periodic table. What I probably should have done is actually written this down. Notes here, but so we're looking for the smaller number. We're looking for the smaller number for ZR, and it is going to be, what is it? 40? 40? Which we got from our periodic table. And then TE is 139, but that's not the number that I really care about. TE is going to be, I'll find it here sometime, 52. Again, the smaller number. That we find on the periodic table. 92 plus 0 is 92. 40 plus 52 is 92. Okay, good. We should get neutron or neutrons on the right-hand side. 238 on the left side. 94 plus 139 is 233. Yes? So wait a second. We got 238 on the left side going to 233 on the right side. What else is produced? How many neutrons is it? It'd be 5 neutrons, right? So now we got 238 goes to 94 plus 139 plus 5 gives me 233. So sure, it ends up being 5 neutrons produced there, plus some energy. Do you guys know where that energy comes from? In both cases, the mass of the products, we talked about this when we did fission fusion, the mass of the products is always going to be slightly less than the mass of the reactants. The difference in mass is what we call the mass defect. Do you guys remember this? Vaguely? The difference in mass is what we call the mass defect. And that mass defect gets converted to energy. Remember we talked about energy and mass being two different forms of the same thing? Like if you have ice, which we had a couple months ago, well now we don't. It's not like the ice just was destroyed. The ice just changed forms. Now it's liquid water or gaseous water. Well, this is almost the same thing. We had matter. Well, now we don't have the matter. The matter has just been converted to energy. That mass defect, the difference in mass, the mass that we lost in this process, is just converted to energy. We're not going to have to calculate that energy, but someday down the road, if you ever did have to calculate, you just use E equals mc squared, right? Take the mass defect and multiply it by the speed of light squared, and then that would give you the energy that was released in that reaction. So that's fission and fusion. Let's rank these actually in terms of a couple of things. Fission reaction, a fusion reaction, a chemical reaction. Let's rank them in terms of energy of reaction, energy per kilogram released, right? Two different things, right? One reaction produces a certain amount of energy, but what if you had the same amount of mass of each one? The energy per kilogram and then the harm. Fission, number one is always high for us. The energy of the reaction of fission is the highest, but if you have equal amounts of fuel, fusion is the highest. And the chemical reaction is always a distant third. Fission, the products are highly radioactive. And fusion, the products are relatively harmless. And we can't really say anything about the chemical reaction because it's all over the place, right? Even a particular chemical reaction. Let's say you're making water. Well, that could be very, very positive chemical reaction, or you could drown in the water. So that chemical reaction could be harmful, depending upon context. Okay, getting there, guys. Almost done, actually. There is a little bit of the Rutherford. Oops, can't even spell Rutherford. I think I would be able to. The Rutherford gold foil experiment, or sometimes the diploma exam people like to call it the alpha scattering experiment. Because that's what we did, right? Is we scattered alpha particles. We took a bunch of alpha particles, fired them one by one at this really, really thin layer of gold foil. And then we just looked at what happened to them. And we found that when we did that most of them went straight through. Most of the alpha particles went straight through. But some of them didn't. Some of them were deflected. And some of them, a few of them, not very many of them, bounced back. What did that tell us? Remember the football field analogy? We had 100 people running across the football field, 90 of them went straight across. That means the nature of the football field was that there was nothing there. The football field was mostly empty space. Okay? The atom is mostly empty space, and that makes sense to us, right? We know that that's the case now. Some were deflected. Well, if positive alphas were pushed away from a straight line path, then these positive alphas must have been pushed away by a positive nucleus. But that nucleus has got to be small, because most of the atom is empty space. Small positive nucleus. Because some of them bounce back, that nucleus must be heavy. Or dense. And that left us with the model of the atom that we call the planetary model of the atom. There is mostly empty space, with the electrons just orbiting around in circles right there. So the nucleus is a small, dense, positive thingy with a bunch of empty space, and then I'm not sure why, to be honest. He concluded that the electrons orbit around the nucleus. I'm not sure where exactly that came from, but or whether it's just like, well, they got to be somewhere. Let's just put them circling around. I don't know. But this, really, this experiment is about the nucleus, the discovery of the nucleus, right? Not the discovery of the electron or even what the electrons do. The main point of it is the discovery of the nucleus. All right, what was that, number 5? Yeah. 6. Oh, this is more. Which sometimes I call the level model, because it talks about levels. Electrons are on. I can't even spell R. And each one is characterized by a specific energy. Man, as I'm going through this, I keep thinking like, oh yeah, I remember this question, I remember that question, that this is going to answer, or that's going to answer, and it's like, you guys are going to ace this thing tomorrow. Oh, I think you will. We did electron level diagrams, right? And clearly there's going to be some electron level diagrams on there. Each one of those levels shows us the energy of the specific level. Now, we also talked about this idea of stationary states. The electrons should emit EMR as they orbit. Because they accelerate, right? Because there's a centripetal acceleration toward the center of the circle. But they don't. So something has to be changed here. Something has to be changed. There's something not right with this. But Bohr would have called it just basically a stationary state, because it's as if these electrons aren't accelerating. They're not emitting EMR like they should. It's as if they're not accelerating here. This is their stationary. And finally, these electrons can make transitions. They can make a transition up by absorbing energy, usually EMR, or they can make a transition downward by emitting energy. And that energy that's emitted is always EMR. Not usually, always. You get a diagram that looks something like this. Now, I'm going to make up some numbers here. It's not hydrogen this time. It doesn't matter. This we would call our ground state, closest to the nucleus, level 2, level 3, level 4. This would be our infinite level with an energy of 0 eV. Let's call this negative 10, negative 2, negative 1, negative 0.5 maybe. I want to say there's 2 or 3 of these on the test tomorrow. I think there's 3. Yeah, I think there's 3 of them. All a little different. Look, we can have a whole bunch of different transitions taking place here, right? We can go from level 2 to level 1. Or we can go from level 2 to level 4. Or we could go from level 1 to the infinite level and ionize it, right? Well, if we're talking about the first one, level 2 to level 1, the energy difference here, the energy of that transition would be level 1 minus level 2, or we would say minus 10 minus minus 2, or minus 8 electron volts. The other one would be, well, we do it the same way, except it would be E4, the final, minus E2, the initial. So it'd be what, negative 0.5 minus negative 2, which gives me 1.5 eV. And if you wanted to find the frequency of the EMR or the wavelength, we just say E is equal to HF, or we'd say E is equal to HC over lambda. And the same thing for the other one as well. Difference is the red one would be emitted, and the green one would be absorbed. Oh, here's the one for you. One more thing with this. Let's just say that we have up to 9.4 eV of energy to be absorbed. Where is it going to go? What level is it going to go? From level 1. Starts at level 1. So we're starting at level 1. We're absorbing up to 9.4. Well, if we start at negative 10, absorb 9.4, that's going to take me to what? 0.6? So what is that, like the 3.8 level? I can't go to the 3.8 level, right? So what is it, 3 or 4? Going to level 3, right? It's like going to 7-Eleven with 245 for a 250 Slurpee. Can't get it, right? You're walking in with a medium. So even though, man, I'm so close, can we just not round that? Can we just not round that up? No. The reason is we can't round it up. It has to be rounded down always. So we're only going to go to level 3 there. That would be our answer, even though we're closer to level 4. That doesn't help it. Yeah. I could use one. I should probably have 2. This is almost over. Good. Oh, we're so close now. So close now. That was topic 6. Quantum mechanical, or the electron cloud. What time is it here? 1:30? Okay, we'll be done in 5 minutes, promise. Or the, well, it was Schrodinger, this guy Schrodinger that came up with this model. SCH, I think? Is there C? Yeah. And there's a couple little dots above the O. Sometimes you see that. Whatever. If you see Schrodinger's name and there's no dots, you'll recognize it. It was the electron cloud, the quantum mechanical model of the atom. Look, you get this nucleus again, and you get these electrons orbiting around. What they're orbiting around is waves. Like this. And what we do is we end up predicting the location based on probability. The quantum process. Probability again. Do you guys remember standing waves at all in Physics 20? You never remember that, standing waves? Like the waves produced in a guitar string when you pluck it? Anybody remember standing waves? I think my video is freezing up there. I see myself standing still on the screen, but oh, there. I just moved crazy quick there on the screen, not in real life. You guys remember that at all? Yeah, don't worry about it. If anybody remembers standing waves and is just afraid to speak up, just so you know, the circumference of this is a whole number of standing waves, so one of the harmonics. You don't really need to know that, but it does demonstrate the clear wave nature of this, is that if you have, remember the first harmonic, second harmonic, third harmonic, right? If you measure the circumference of this, the circumference would be the length of a whole number of harmonics. We already know that electrons are waves, but just more proof for that. I think probability is still wrong. Is prob A? Is it A? It's not A. It's A. Finally, last thing. What to the Z? Sometimes I call these sub atomic particles. It's really what we do is break, if we can, break subatomic particles down further. We went through that whole chart yesterday, right? But really what you got to know from it, like that was important for giving you the big picture of things. But today, I mean, what do you got to remember for the test tomorrow? What do you got to know for the test tomorrow? Well, there's leptons, which are fundamental particles. They can't get any smaller. And there's different types of leptons. There's the muon, and there's the muon neutrino, and the anti-muon, and there's the tau, and the anti-tau, and the anti-tau, anti-neutrino, and all those. But the ones that we really care about, the example would be the electron. And the positron, right, which is the anti-electron, and the neutrino, the electron neutrino, and of course, the electron anti-neutrino. Muons and tau particles also have neutrinos and antineutrinos, but whenever we talk about a neutrino or antineutrino in physics 30, we're talking about the electron neutrino or the electron antineutrino. Now, the other type of particle was the hadron, and these are particles that can be broken down even further, made up of quarks. And examples of those would be the proton and the neutron. If you look in the bottom right-hand corner of your data sheet, you can see an up quark has a charge of positive 2/3 of the elementary charge, and a down is negative 1/3. An anti-up is negative 2/3, and an anti-down, is positive 1/3. You don't even know those numbers are on your data sheet. Know that protons and neutrons are made up not of antiquarks, but of quarks. If they were made up of antiquarks, they wouldn't exist for more than a fraction of a second, right? Because they annihilate. And they're always made up of 3 quarks. So a proton and a neutron, they always start with an up quark. A proton must be up, up, down, because it's 2/3, 2/3, and negative 1/3 gives me 1. And a neutron must be up, down, down, because, yeah, those 2/3, negative 1/3, negative 1/3 gives me 0. Now, it doesn't mean just because like we only looked at these, it doesn't mean you won't have to use these. But it means you don't have to remember anything about that. Does that make sense? Like, we give you questions all the time where you have to apply what you've learned. You have to remember, or at least be able to figure out that a proton is up, up, down. But you may very well have to figure out something involving anti-up, anti-quarks as well. But you'll be able to figure it out. You don't have to know anything other than the charge of the anti-up and the anti-down, anti-quarks.